So now we've taken a look at light in a little bit more of a complete way. So we've got this idea of light as a wave, we have this idea of light as a particle or a photon, and we're starting to hopefully see a little bit as to kind of why the theory is as complicated as it is, because light isn't simple. Sometimes it behaves exactly like a wave, but sometimes that wave model doesn't explain things we observe in real life. And so this brings us to how all of this connects to matter. I mentioned it very briefly when we talked about black body radiation, but we haven't really gotten into why. So the other big problem that was facing scientists back in this day, and so we're talking about the early 20th century, the early 1900s, late 1800s is kind of when scientists were grappling with these problems. And so we come across what's called the atomic spectrum. And so the idea here is that we have a tube filled with a gaseous element, very similar to an old-fashioned like fluorescent light bulb, where you have the tube full of material, and when electricity is passed through it, it starts glowing. And what's interesting is if you fill your light bulb, your fluorescent light bulb, your discharge tube, whatever you want to call it, if you fill that up with a single element, some interesting things happen. So if I do this with hydrogen, I fill the tube with hydrogen only, I flip on the switch, electricity starts passing through my hydrogen gas. It will start glowing kind of a purple color. But if I take that purple light and I pass it through a prism, or a diffraction grating that separates the light out into its component colors, what I get is really sort of fascinating. I get a very specific frequency and color of red at 656.3 nanometers. I don't get any other colors of red. That's it. I get one very sharp, precise color of red. I also get, and I will admit that it's a very bluish green, but I get a very sort of teal, aqua, blue-green color at 486.1 nanometers, which I'm going to, for reference, just call green for right now. I realize it's not as Crayola green as we might like, but I'm going to call it green. I also get a bluish-purple light, which I'm going to call blue for the purposes of this discussion, at 434.1 nanometers. And finally, I get a really deep shade of violet, which I'm going to call purple for the purposes of our discussion here, at 410.1 nanometers. Those are the only 4 colors of visible light that hydrogen produces. All of the other colors in between are missing. There are these gaps in between. And so the light that is emitted by atoms appears to be quantized. There are only certain allowable values for frequency, wavelength, and energy that I can get out of these atoms. Now, of course, the visible spectrum, or the entire rainbow, sort of looks like this here in the middle. There's the visible spectrum, or the entire rainbow. Helium, this is not showing up particularly well on my screen. I don't know if it shows up better in the video or not. But helium also produces some very faint colors, and they're in there. You can kind of see one of them right here, although its line is not real obvious. And I don't remember exactly how many colors helium produces, but there are definitely some lines on there. Again, I'm only seeing really one on my screen here. If we look at iron, iron produces a lot of different colors. Now, the other thing to consider is that we are not seeing all of the light that is produced. Remember that only a very small chunk of the light is visible to the naked eye. And so if you actually look with instruments at the hydrogen spectrum in a little more detail, you get lots more in the ultraviolet range, and you also get lots more in the infrared range as well. So hydrogen actually produces a lot more than 4 colors, but it only produces 4 colors of visible light. And so it turns out that every element has kind of its own fingerprint of light that it emits. Again, only some of it is visible. So this chart here in the middle tells me that helium is not producing a whole lot of visible light, although when I zoomed in I was able to see at least one line. I think there's more than one line, it's just really faint. Iron produces lots in the visible spectrum. And so you can get online and look up the spectra of other elements, and in the lab we actually will take a look at several of the elements. So the problem was, what gives? Why is this happening? And so in the late 1800s, a guy by the name of Balmer came along, and he was able to create a formula mathematically that predicted all of these different frequencies. Another scientist came along after Balmer and developed the equation even further, and it's now called the Rydberg formula and the Rydberg constant. But it's a formula that is completely empirical. There was no scientific model of the atom that this is based on. This is simply based on numbers and patterns. They were able to just measure the frequencies and figure out mathematically what the pattern was. They didn't attempt to explain it physically at all. What is the atom doing? What are the electrons doing? What are the photons doing? There was no theory to accompany it. But the equation looks like this one here. And this is an equation that I would provide to you. This is not one you would need to memorize in this course. But we can see that it's 1 over lambda, so there's our wavelength. And then we have this constant. This is our Rydberg constant. And again, constants are always provided, so you don't need to memorize that either. And then you've got these two n values. These are just integer numbers, like 1 and 2, 2 and 3, 3 and 4, 5 and 2, right? Any different combinations of whole numbers. Again, I'm not going to put decimals in for my n's. These are going to be whole numbers. Are going to give me, so if I just put in different n values in different combinations, 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, etc., I start to get all of the different wavelengths that hydrogen produces. In 1913, a guy by the name of Niels Bohr came along, and he actually proposed a model for the hydrogen atom that explained this behavior. Scientists at the time thought that the electrons were actually orbiting the nucleus the way that a planet orbits a sun or a star. And we now know that this isn't true, but the Bohr model is somewhat simple to look at, and so I think that's why we start here. The actual model of the atom that we understand today is a little more complicated, so we're going to build to it. So we're going to start with the Bohr model, even though we know that it's not 100% accurate. And what Bohr basically said is that you have your nucleus in the center with a positive charge, and you have your electron that under normal circumstances is going to be at a fixed distance from the nucleus. Kind of like an orbit of a planet, except remember that the atom is three-dimensional. So our solar system looks a little bit more two-dimensional than this, kind of like I'm drawing flat on the picture here. So remember that this is three-dimensional, but that the electron is staying a fixed distance from the nucleus. Whether it's moving in a straight curved orbit path or not, at least it's staying a fixed distance from the nucleus. And that's what he said. And so he called this distance n equals 1. And it has the lowest energy, and so n equals 1 is called our ground state. Bohr then went on to say that if we bump the electron out further from the nucleus, each successive distance further out, we're going to give a new n value. So this is n equals 2. And then what happens is these distances start getting closer and closer together. So there's 3, there's 4, there's 5, etc., 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 and we can keep working our way out. And we'll see this on the next page, but these distances start to get closer and closer and closer to each other. And so we reach this kind of limit to how far the electron can really go and still be associated with the atom. If we push the electron too far away, it's eventually going to be ionized. It's going to leave, and the atom would then have a positive charge. So there's this upper limit to how far we can push it. And so each of these n values gets closer and closer together. All of these electrons, or all of these states that are further than n equals 1, are called excited states. And so what Bohr was able to say, let me see if I have this on the next page. There we go. So what Bohr was able to say is that when an atom absorbs energy, endothermic, that bumps the electron up to a higher energy state. So if we think about our atom here, and we think about our electron here at n equals 1, if I add some energy to it, that will bump the electron out to this larger energy state, which I might call n equals 2. And so now I have my excited atom. The flip side is also true, that when an atom releases energy, again, for example, light, if it radiates heat away from it as light, then the electron will fall back down to its lower state. So we have our endothermic and our exothermic process. You can see in the figure on this page that the energies get closer and closer and closer to each other, like I showed you on the previous page. So notice the jump, these are our n values here. So from n equals 1 to n equals 2, notice that this jump is by far the biggest. The jump between 2 and 3 is shorter. The jump between 3 and 4 is shorter yet. The jump between 4 and 5 is really short. And eventually, we reach this upper threshold limit where the n value approaches infinity. And this actually represents our reference zero energy. That's the highest energy that an electron can have and still be associated with the atom. If the electron's given more energy than that, it will actually escape and the atom will become ionized. And so all of the other lower energies are measured as negative numbers relative to that. Now, I do want to mention a couple other quick things before we move on to examples here. Again, the Bohr model has holes, and so we're going to get into those in a little bit. We're first going to practice working with the Rydberg formula and Bohr's model here a little bit. The biggest limitation that Bohr's model has, so actually let's write this down. Bohr's model. The biggest problem that it has is that it only works for hydrogen. Technically, it works for any single electron system. So theoretically, I guess it could work for like helium plus, if a helium atom were to lose one of its electrons, or if lithium were to lose two of its electrons, but those aren't stable typically. So in practice, the only thing that Bohr's model is really particularly good for is hydrogen. And the other thing is that electrons do not orbit the nucleus. So we'll get into that a little more on the next page, but I just want to make that clear, that we're not going to stop and say that this is current theory. This is kind of an older theory. It's got some problems, but it is a quantum theory, and it does help us, at least in a basic sense, kind of understand what's happening to the electrons when energy is absorbed and released from the atom.